Hello and welcome to the podcast on calculating the pH of buffers. This is just the practice problems. The previous recording is the actual notes where I go over what the different equations are and what the different components are. So you may want to go back and watch that. Alright, so what I would recommend for this video to get the most out of it is to pause it here to try the problem on your own, and then you can play it to either see if your answer's right or if you get stuck to see how I solved it. So let's take a look at the first practice problem. It's very important when you have a buffer to determine what you have and to figure out what you need to do to solve the problem before you actually really start diving into the numbers. So let's take a look at the two chemicals that we are mixing here together. So we have here a salt, and we know that Na is going to be a spectator ion, and so we're going to be left with NO2. So this would be a basic salt, so a salt that contains a conjugate base. And to this we're adding a strong acid. And anytime we're adding a strong acid, or if we were adding a strong base, in some cases, it would cause a chemical reaction. So the chemical reaction that takes place here is between the conjugate base and the strong acid. So we're going to form some of the weak acid from this reaction. And if we notice, the reaction arrow only goes one direction because we have a strong acid that drives the reaction to the right. And so because of that, we end up with the conjugate base and the weak acid, which is what makes this a buffer. All right, so the other thing that I think a lot of you guys are having trouble with is, would I use the Ka version of this equation, the pH equals the pKa Henderson-Hasselbalch, or would I use the pOH with the pKb? And either way will give you the right answer, but I think one way sets you up for a lot easier of a problem. We do not know the Kb value for NO2 minus. There's no chart that would tell us that. So in order to get the Kb, we would have to convert it from the Ka. So I think it's a lot easier, since you have, in the end, the conjugate base and you have the weak acid, so you have both anyways, just to go ahead and use the pH version with the Ka. So all right, now we need to figure out our amounts. So we know that we need to get these into moles. Since we're adding two volumes of a liquid together, that's going to change their molarities. So it's a lot easier just to use Henderson-Hasselbalch in moles. So I'm going to take these two values here and multiply them together. So 40 milliliters would be 0.04 liters times 0.1 is going to give us 0.004 moles. Okay, and because I know this is the conjugate base, I'm going to label this my A minus, okay? And then we have here 10 mils of 0.1 molar, so that's going to give me 0.001 moles, and we're going to make that H plus because we know that Cl minus is just going to be a spectator. And so now we can put our values right underneath of the equation to do our calculations, because a chemical reaction is going to take place, so our amounts are going to change. So underneath of here, I'm going to put, let's see, 0.004, 0.001. And this you have negligible amounts of to begin with. So the H plus is going to be our limiting reagent. It has to be the limiting reagent, the strong acid or the strong base, in all of these problems, because if it's not, you're not going to end up with a buffer. You would just end up with the strong acid. So now we're going to add this to the other side. So what we use up of these two, we form this. That's the whole goal of a chemical reaction here. Okay, and so we're going to get 0.003. This is used up. 0.001. All right, so now we have our HA and we have our A minus. And so now we can go ahead and solve this. So let's label this our A minus, let's label this our HA, and we can plug this into Henderson-Hasselbalch. So we've got the pH equals the pKa, so that's going to be the negative log, and we know the Ka value for this because we can look it up in that table. Okay, plus the log of, and it's always A minus over HA, so we would have 0.003 over 0.001, and now it's just a matter of plugging it into the, and once we plug it in, we get the pH is equal to 3.88. And again, I know I've explained this before, but this is really important to understand. Even though we started with a conjugate base, okay? So if we just have this solution, that's obviously going to have a pH above 7. But when we mix the two of them together, we end up with a pH that is acidic. And the reason why that makes sense is because we have both a weak acid and a conjugate base mixed together in order to make this pH. And what this tells us is that the weak acid is stronger. It's still a weak acid, but it's stronger than its conjugate base. All right, so now let's take a look at another example. So we need to label what we have. So what we have here is a weak base. Okay, and that NH group, that amine group right here gives it away. And to it, we're adding a strong acid. And so this is going to cause a chemical reaction in which your weak base reacts with the H plus, your strong acid, and it forms the conjugate acid. So now we have the conjugate acid and the weak base. That's what makes it a buffer. And of course, the amounts will work out so that we have both in solution. All right, so now if we take 100 mils times 0.2, that's going to give us 0.02 moles of our base. I'm just going to label it B because that makes life easier. And we're going to end up with 0.012 moles of the H plus. And let's go ahead and add that in here. So we have 0.02 moles, 0.012, and negligible amounts. So our limiting reagent is going to be the H plus, and we're going to subtract that. We can see that because it has the smaller amount. You also know it has to be that because otherwise you don't have a buffer. 0.012. So we end up with 0.008. None of this is left, and then 0.012. All right, so now because we have a weak base, we're going to want to plug this into the Henderson-Hasselbalch POH equation. Let me write this up here a little bit. So our POH is equal to the negative log, the pKb, and the value for that, when we look it up on the chart, is 4.38, that's a decimal point by the way, times 10 to the negative 4 plus the log of, okay, so let's go ahead back here and label this really quickly so we make sure we're plugging it in the correct way. This is our BH plus, our conjugate acid, and this is our B. And so we're going to put this value on the top. These decimals really don't want to show up. Over our B value, which is 0.008. Okay. Okay. And so now we just plug it into the calculator. Okay, so in this case, we're going to get the POH is equal to 10.47. Oh, wait a second. That's actually, scratch that. That's already sorry, I already found the pH. So the POH, when you plug all of this in, sorry about that, you're going to get 3.53. So I plugged that into the calculator. And then when you subtract it from 14 to get the pH, I just kind of naturally do that, we're going to get 10.46, 47, something like that, okay? 46, 47, somewhere in that range. Okay, depending on how you round it. Okay, so let's try one more problem here. So let's label what we have. So in this case, we have a salt, okay, and we know that the NO3 is a giveaway for that. And we know the NO3 is going to be a spectating ion. So we're going to come in and put a plus charge here for our cation. Okay, and because this is a cation that we're left with, that means it has to be a conjugate acid. And to the conjugate acid, we're adding an amount of NaOH, and that's going to be a strong base. So that's going to cause a chemical reaction between the conjugate acid and the strong base. So our conjugate acid is here, our strong bases here, and that's going to react. Again, it's only going to go in one direction, and it's going to reform the weak base, and then we make water, which water we don't really care much about because we've got a whole bunch of it. So let's come back here and figure out our amounts. Now, in this case, we're starting with a conjugate acid, but like I've explained before, it's going to make a lot more sense to use the KB version, the POH version of Henderson-Hasselbalch, because we don't know the Ka value for this. We would have to convert it. So then we would be converting everything over, and that just gets very confusing. So I say since we've got a KB, let's calculate it in KB. Plus remember, we're reforming the weak base anyways, so we're going to have an amount of that at the end of the reaction. So now we're going to take our values here and multiply them. And I made this 1 molar just to make the calculations and our lives a little bit easier here. So this is going to be 0.03 moles of the BH plus, which is our conjugate acid. And if we take these two and we multiply them, we should get 0.02 moles of the OH minus, because Na, of course, is our spectator. So we've got 0.03, 0.02, none, 0.02. This obviously is going to be our limiting reagent. It's going to get completely used up. And whatever we lose of these, we're going to make of these in our chemical reaction. So we've got that gets used up. We've got 0.01 of this. Whoops, there's an extra 0 there. 0.02. Okay. So now I'm just going to plug it in. So we've got, and let's actually, before we do that, let's go back through here and label these. So this is going to be my BH plus, this is going to be my B. This is a really important step to go back and label, because however many millions of these problems I have done, I still make mistakes if I don't go through and just label what I've got before I plug it in, because there's a lot of numbers to look at. So we've got POH equals the PKB, so we'll do negative log the KB for this. We look up on the chart, times 10 to the negative 4, plus the log of, okay, so now we've got this, the conjugate always goes on the top, so that's going to be 0.01 over 0.02, okay, and then we're just going to plug it into the calculator. Alright, so we find the POH is equal to 3.06, and I just plugged it into the calculator. So we just have to remember to subtract from 14. And it's harder to remember with the buffers to subtract from 14 because your pH could be above 7 or below 7. So there's no way to really check. You just have to go back and make sure that you did that last final step. So we find that our pH is 10.9. And again, even though you started with a acid, that's okay because you also formed the weak base. And this just lets us know that our weak base is stronger than the conjugate acid. Okay, that's the end of the practice problems for now. I hope you have happy studying.